Hi everyone, thanks for joining us for the webinar today on the DevOps 2.2 Toolkit. I just want to let you know a few things up front before we really begin. So one is we are recording this, so anyone who may have a colleague who wasn't able to join or maybe you missed part of it, you will receive an email with the recording soon. The other is we are able to take questions. We will have time at the end, so please, as soon as you think of questions, ask them. Even if you think maybe we won't have time, we can always take them offline if need be. So please, as soon as you think of something, just put it right in there and we'll get to whatever we can at the end. We do have a fair amount to get through, so I don't want to take up more of your time. So let's get started. Introduce you to your speaker, Viktor. Viktor, here you go.
Thank you, Max. Okay, so first, a very quick introduction. This is me. Those of you who haven't seen me, this is how I look like in best of the days. I work for CloudBees, obviously. I'm one of the Docker captains, so I'm present in both communities in a fair quantity. I have a blog, Technology Conversations, read it, some courses, some YouTube videos, a lot of books, buy them, and a Twitter, please tweet, that's all okay. So that was a very quick introduction. So now, last few weeks ago, I had a similar webinar here where I explained where I think that we are as industry and where we are going as industry regarding infrastructure and services, architecture and deployments and so on and so forth. And that is kind of an intro into what I'm going to speak and explain today. So I'm going to skim through the material from a couple of weeks just in case some of you were not present. It will be very quick without much explanation. Starting with what we really want is to set up infrastructure and services in a certain way that they have certain qualities. In case of infrastructure, today, and today is 2018, we are all looking into using, trying to skip all those tools and use immutable infrastructure, meaning that we are building images that are much more reliable than provisioning servers at the runtime, and we're instantiating those images in whatever quantity we want. We moved away from treating our servers as pets, but simply as numbers, as cattle. Average company, the number of servers in an average company increased drastically. We have really huge quantities of service to manage these days, and we cannot do it as we were doing that before, meaning that servers are now numbers. We're not emotionally attached to them anymore. Everything is becoming self-service. Doesn't matter whether you're hosting on-prem or you're hosting in cloud, one of the cloud providers, your developers, and everybody in your organization expects that all horizontal departments are working in providing some kind of a service to others instead of waiting, being reactive and waiting for issues to be opened and then fix them and all those things. Everything is dynamic and elastic these days. There is no more static infrastructure. Such a thing is thing of the past. Even though I still see those things in many companies, it should disappear fairly often, hopefully. And everything that is repeatable is fully automated. That's where we are today. Not necessarily that's where everybody is today, but I think that's where industry as a whole is today, or at least is trying to get to. Now, if we move to services, we are moving away from monoliths and into microservices. Sounds like microservices actually the name. We are moving into something that is smaller and more manageable in relatively small teams and is decoupled from each other. We are moving into immutable deployments. Everybody these days knows what Docker is and the benefits it provides, and why immutability is so important. And just as with infrastructure, all our services are dynamic and elastic. They're moving around our clusters, being scaled up, scaled down, and finally all our processes on service level are automated as well. And that leads us to where I think that we are going to get where we are partly today and we are trying to get tomorrow, and that's building self-sufficient systems that are capable of operating without humans. That does not mean that I'm predicting that humans will not be involved in the process. They definitely will, but on a creative side, not on a repetitive side of doing everything the same over and over again. And to that, we had an analogy of imitating human body, where everything is relatively small cells, many of them able to scale up, scale down, replicate themselves, and so on and so forth. Self-healing today is a solved problem. That's not something really that is discussed these days, because we have the Kubernetes, we have Docker Swarm, we have Mesos, and so on and so forth. All those tools are providing us more or less out-of-the-box self-healing, meaning that our applications will be in a desired state most of the time. And if you move that discussion to infrastructure, to our servers, all cloud providers provide that as well through auto-scaling groups. In case of AWS and whatever is the name in Azure and GC, they all have the same features in that aspect, and they're all guaranteeing that our both infrastructure from vendor perspective and services from container scheduler perspective are guaranteeing that things are up and running almost all the time, and that desired capacity is fulfilled at any given moment. Now, where I think that the subject we will be discussing throughout this year and probably the next one is self-adaptation. How can we go beyond self-healing? How can we have systems that not only are trying to fulfill the desired capacity and desired specifications and so on and so forth, but how can those systems adapt accordingly, depending on influences that are happening both inside our clusters and from outside? How can we scale up depending on the traffic, or scale down when a lack of traffic? And how can we basically adapt continuously, be truly elastic in a fully automated way? So that was a very quick recap of the talk from a couple of weeks ago. So what I wanted to show you today is how I think that such a system can be designed. Many of the things you probably saw already, many of the things you might be using, some of the things you probably might be new, depending on where you are right now. I will mention a few tools in the process, but I will do so only as a way to demonstrate certain capability or certain feature, not because I think that that tool should be used and only that tool. Everything I'm going to mention today can be replaced by at least 20 tools. It's about principles and what each of them should do. So at the beginning, we have a cluster, right? A cluster in this case is something more ephemeral. It's simply a collection of resources of all the servers that we have, right? I don't really care how many servers we have. I don't really care what are their individual sizes. What we really care when we talk about clusters is what is the total amount of memory, what is the total amount of CPU, how much disk space we have, external disk space, hopefully, what is the speed of network, and so on and so forth. We don't really care about individual clusters. That's the thing of the past, more or less. At least in most cases, we don't. So we have a cluster which is a collection of resources, and that cluster is always inside of some virtual private cloud or some firewall, some network that isolates that cluster from the outside world. And inside of that cluster, we always, at least with all the schedulers we have today, we have always managers in one capacity or another. They're simply servers. They're making sure that the cluster is always operational, that they're performing service discovery, gossip protocol, and all those things that modern master servers do, like Kubernetes, Docker Swarm, Mesos, what's not. The only important thing about them, most of the things they do by themselves. We don't need to worry much about what they do. I mean, we should know what they do, really, but for the purposes of user experience, that's not really important. What really matters is that there's always a node a number of them. It's never 1, it's never 2, it's never 4. It's 3 or 5, maybe 7 masters. It needs to be odd number because of quorum. All those masters need to agree on any piece of information. And the only way that they can agree on something is that if there is a majority of them with exactly the same information. And we cannot have a majority with, let's say, 2 servers, because if one of them dies, goes down, and sooner or later, every single server goes down. If one of them goes down, then we lost quorum because we have only 50%. We don't have over 50%. We don't have 50% plus 1. So 3 managers, that's every cluster. That's what every cluster has these days. It can be called master, it can be manager, but they're kind of lead servers. And they're all inside of some auto-scaling group. Now, as I said before, today I will use terminology from Amazon Web Services. You can translate that to whatever your hosting vendor is, Azure, GC. They all have the same thing, just different names. But the point is that servers are never. We don't create servers anymore. We don't send commands like create me 3 servers. I want 5 servers. I want you to do this. I want you to do that. We are moving away from imperative way of handling things into declarative, and declarative in case of AWS, for example, is creating auto-scaling groups, which we specify. I want you to give me 100 servers, and no matter what happens, I want you to always have 100 servers, and it will just happen. And if 2 of them goes down, auto-scaling groups will make sure that 2 new servers are created. They will maintain the desired state. That's self-healing in itself. That's again out of the box. And then we have certain number of workers. Workers are all the other servers inside of a cluster. Whatever you want to call them, they might be nodes, they might be workers. They're simply where we host our applications. That's where they are running. Now, this is all easy so far. We have some kind of registry where we're going to store the state of the cluster. And the reason is very simple, because auto-scaling groups are not enough. When a new server is created, it needs to somehow find out about the rest of the servers, about the rest of the cluster, and usually we store that information in some kind of a registry, which can be DynamoDB or S3 in AWS. It can be Git, it can be wherever, as long as new servers that are created by auto-scaling groups have a way to fetch information how to join the cluster. And finally, since our services are so distributed these days and they're continuously moving up and down and left and right, they're being scaled. Every modern cluster needs some kind of software-defined network, usually called overlay network, which will allow all those services to communicate with each other without knowing their individual addresses. So what else? Now, since we as industry, we cannot move away from stateful applications, we need a network drive as well, because these days it's simply silly that we expect that we store anything on those servers, on those worker servers or managers, because we must assume that they will go down. So the only way to store the state somewhere, if we are now focused only on storing state on a disk, means that it needs to be stored on a network drive. So every single server needs to, or a container, or whatever you're using, needs to have a network drive to preserve the state and make it fault tolerant in case of any of the servers go down. Now we're coming to what happens when a user wants to access those servers, what happens when they want to access one of the applications. That means that we need some kind of load balancer. But in my case, I think that load balancers changed drastically. Actually, they didn't change from technological perspective, but the way how we're using load balancers changed a lot, in terms that load balancers are not in charge anymore of sending requests to our services. They're not in charge of anything anything beyond simply finding a healthy server. The only purpose of load balancers these days that are sitting outside of SDN is just to find, okay, I'm going to forward this request to any of the servers that are healthy, because I know that software-defined network will take it over from there and forward once again to wherever the application actually is running. Simply load balancers are not capable of handling that high level of dynamism. They're not capable of really understanding what's going on inside of our clusters, but they're more than capable of understanding what are our servers and how to get to them somehow, and then forgetting about all those requests. Now we're coming into interesting part, the part that I think that changed drastically in the last couple of years, and that's that if we want to build a cluster that operates without us, if you want to get to the point that we are not needed at our work anymore, first thing we need to start thinking about are metrics, right? And collecting metrics changed, I think, drastically in the last couple of years, simply because everything is becoming much more and more dynamic. So that means that all those old tools like Sensu, for example, are really not being able to handle that type of work anymore. So we're seeing a big push towards new things like Prometheus or maybe InfluxDB. But no matter what, they need to be equally capable of discovering the servers if you're still focused on infrastructure, and being very highly dynamic. But no matter how they do, what they do, the point is always that they need to collect all sorts of metrics about infrastructure, CPU, memory, disk, hard disk, and so on and so forth, and store it efficiently somewhere. And then we have the part of getting to the point of what we do with all those metrics. Because obviously, if you're talking about large scale, we cannot simply watch dashboards. We cannot simply sit in front of monitors and observe what is happening. We need a relatively sophisticated, maybe alerting mechanism that will send alerts, dispatch those alerts whenever certain thresholds, whenever certain expressions are evaluated and then end up being true, wherever certain things are happened, no matter whether those things are some things that we predicted or unpredictable things, we cannot know that in advance. But no matter what the thresholds are, we need to dispatch those alerts and send it to some kind of executor. In this case, I tend to use Jenkins because I'm familiar with it, and I think it works pretty well as a general executor of I can run anything I want, and that something can be executed through an HTTP request, which is what most dispatchers support today. So, and then what happens when such an alert is fired? Let's say that not enough memory, the total memory of the cluster is beyond 90% in total, or there's not enough CPU, or maybe there is too much CPU, and we want to reduce them. In any case, that executor, whichever it is, in this case, communicates with AWS API, or it can be GCE or Azure, and modifies the auto-scaling groups. Again, we are not destroying clusters directly ever. We are not creating, we're not destroying servers. We're not creating servers or anything in between. What we are always modifying are auto-scaling groups and letting the system behind it, let's say AWS, manage whether servers should be created or they should be destroyed, and so on and so forth. So in other words, the result of those alerts from an infrastructure perspective is that the system itself changes the desired state from something to something else by modifying auto-scaling groups. So our desired state is fluctuating all the time. Now we need 100 servers, an hour afterwards we need 95, and then we will need 110 again. And then, that is fully automated, right? There is no real reason why it shouldn't be fully automated, because those are all relatively predictable and easy to define conditions. It's more like a mental challenge that we need to unlearn what we learned before than a real obstacle in what we have at our disposal today. But then still, some unexpected things will happen, and when they do, then just as humans recuperate from whatever, most of these diseases that are attacking us every single day, our body is recuperating by itself. It's fully automated, but every once in a while you need to go to a doctor just in case because something unexpected happens. And the same thing is with the system. So it cannot be truly self-adaptable, self-sufficient, but it can be in a fairly high level. And when unexpected things happen, when a system cannot fix itself, and I think that it can in maybe 90% of cases, but those, or 95, but those 5% of cases when unexpected things happen, then we send a Slack message or maybe an email, HIP chat, or whatever communication method you're using, does not really matter. So more or less, with if we set up all those components on infrastructure level, we have something that in most cases will operate without the need for us. When I say us, you, me, humans, need to touch anything. It will be continuously recreating the services that fail. It will be creating new ones, destroying when we don't need them, and so on and so forth. So let's move into services, right? How can we make our applications themselves behave in a very similar way? And I think that we're still a bit further with on infrastructure level than on services level today in terms of tooling. So of course we need a cluster where we're gonna host those services, and in this case I'm gonna split the images into two domains. What I think that are things that humans should do, and the machine domain, which are the things that I think people should not meddle with. That's not where machine domain are all the actions, all the processes that should be executed fully or almost fully by machines, and where we should just give up of trying. So of course, a developer, and when I say developer in this context, I mean basically almost anybody in our organization. Anybody who commits anything to Git is in my book developer. That can be a tester, can be operator, can be even analyst. I don't really care. To me, all those are, I'm just putting them under the same umbrella of developer, meaning a person that puts something in Git. And as a side note, if it's not in Git, if it's not in code repository, it should be treated as non-existent anyway. So everything is there, we push it there. And then in this case, executor, let's say Jenkins, picks up that there is a change in code repository and needs to do something with that change, whatever the change is. It almost always some action needs to be executed on every single commit. And in this case, since we are all living in the era of schedulers, Kubernetes, Docker Swarm, Mesos, no matter what you're using, that action of pushing something to code repository always ends up there. And I intentionally say ends up because there are many steps that such an executor needs to do before. We need to build build some artifacts, run some unit tests, run some functional tests, integration tests, performance tests. We might need to deploy to a test cluster first and run a round of tests, and then end up finally in production. And there may be many steps in between. But what they all have in common, that they all end up in the same spot, and that spot is some kind of a container scheduler which receives instruction. There is a new tag, there is a new release of something, execute rolling update of that something, or create that something if it doesn't exist somewhere inside of a cluster. That's what schedulers do. So no matter what was the original intention, we built something, and that something ends up being deployed to our cluster. And now, the part that is still, I think, missing in out-of-the-box tooling is that we need somehow, actually depends from one tool to another, but in any case, we need something that is listening to those events, something that is listening to instructions that were sent by Jenkins to the scheduler, and deciding to do some extra actions, to do some extra steps that were not necessarily done by scheduler, because scheduler, after all, has one main purpose, and that purpose is to deploy containers or update existing containers and make sure that they are always running under desired capacity. But then that type of listener might need to go to the rest of the system and reconfigure the proxy, let's say, or maybe reconfigure your Prometheus instance, or maybe reconfigure Jenkins itself. It needs to do some actions so that the rest of the system complies with the change that we did in code repository. We cannot expect anymore that we have a request like, oh, infrastructure department, please reconfigure my proxy, or this department, please do that, right? We need to assume that once that commit is pushed, and that can be every minute, maybe the whole system needs to change. The whole system needs to update and make sure that it is working according to the new specification, to whatever the change is. And if we want that to be automated, if we want all that to happen without humans, we need to listen to all those events and act accordingly. And we assume that in most cases, we would assume that all the additional information that is required is provided as, let's say, probably most likely labels of that service that was deployed. Now since Prometheus is, let's say the Prometheus is reconfigured and it understood, okay, there is a new service. You just deployed something to my cluster. It will start sucking metrics from that service, and it will probably combine those metrics from that service with metrics from more journalistic exploiters, those that I mentioned before, like CPU, memory, maybe information about containers, and so on and so forth. So we combine always general high-level metrics, not necessarily high-level, but general metrics that can be applied to anything, with the metrics very specific to our services, and gather all that into some kind of database like Prometheus. And then we're coming to the pretty much same process as with infrastructure. All those services, all those things happening on application level inside of our cluster is generating some data, and that data is continuously evaluated against often a very huge number of formulas, of expressions. And those expressions, when they meet certain criteria, are sending alerts saying, okay, look, your application is too slow. Response time during last 3 minutes of 99 quantile of this for this application is above half a second, right? And that's disastrous. Nobody wants to have such a slow response time. So we're going to need to do something about that. And that something, again, is sending back a message to executor, whichever it is, Jenkins, and saying, okay, so this service is suddenly became too slow, or maybe it suddenly became too fast, let's say. Do something about it. Where all that is processed, all that is evaluated. How many replicas are we currently running? Excellent. How much? What is the increase rate we are expecting? So on and so forth. Makes a decision, and that decision is on a scale from 17 to 25 of that service. And that information is again sent to a container scheduler, which says, okay, oh, so you want to run more replicas. Now we're coming to the other part of the story. Now we have a user, that is a person or a persona that is actually using what we're producing, right? Because it's kind of more or less pointless that we do what we do without anybody using it. Our application, UI in browser, backends, frontends, whatever you're doing, somebody is using that, right? And that somebody needs to be able to access. And remember, this is a cluster. It's highly dynamic. We don't know where the servers are. We don't know their IPs. All we know, and we don't know where our services are running. They're continuously shifting. So those requests are always sent to some kind of networking. In case of Kubernetes, those would be services, maybe combined with Ingress networking. In case of Swarm, it would be overlay. Anyway, requests are sent from DNS, probably through external load balancer, into any of the servers of the cluster, and that request is picked up by networking. It has more or less singular purpose, and that purpose is find me where is one of the replicas of a service that should respond to this request. It finds that service and sends it, finds that service and forwards the request to it, and then it goes back to where it came from, to the user as a response. And if all that fails, if you cannot fix the error, just as before, alert dispatcher, alert manager would send the notification to Slack and say, okay, you messed up something, to developer, you messed up something, fix it. There is a problem that the system itself cannot solve. Okay, I just realized, guys, that I spoke very fast, much faster than I hoped, and we have a lot of free time. I just finished my presentation much faster than I hoped. This is my Twitter handle. It's okay if you say that this was awful. This is my blog, Technology Conversation. This is something and something else, and then there are books. And now we have approximately 15 minutes for questions. And I see a hands raised. Jean-Marc.
So if you have a question, please put it in the question panel. I saw one or two basic ones come in earlier, but if you have any, please let us know. We'll wait another minute or two to see if anything comes in. Here we go. Did you see, hey Victor, did you see, will SDN support co-location across countries?
I didn't see that. I'm looking at the chat. I don't see that message, but okay, if you can read them, then I don't need to see them. Will SDN support across countries? I assume that means across regions. That's a bit tough because, I mean, SDN itself can support it, but that's not your problem. The problem across regions is that there is often very big latency, and that would slow down everything to crawl. Now, SDN between managers or masters, that should definitely be co-located in the same region, because latency would definitely affect it negatively. Now, I would guess that for worker nodes, that should be about to get solved, I think. Even it will never be fast because of the latency, but I would rather say that if you need to run something across multiple geographically separated regions, probably something like Kubernetes Federation would be a better choice than a single network spanning all those regions.
All right, thank you.
Can you speak? I just saw that there is a question section, and I was reading chat section. Sorry. Great presentation. Explain more about how Sensu is insufficient lately. Okay, so it has a couple of problems. First, it does not really work well, at least from my experience, and I might be wrong, with the dynamic nature of applications in cluster. So it somehow expects that things are more or less static. I know that you can use tips and tricks to make it not be kind of dynamic, but it's not really as feature rich from the point of view of elasticity as others like Prometheus are. And the second thing that I don't like about Sensu is that it's mostly unidimensional. It does not provide enough information. It's more designed, even I know it's not 100% like that, but it's more designed towards being binary. Something is true or false, than really providing, okay, this is a metric, and these are the 50 labels associated with that metric, or in 5 different dimensions, so that I can actually query the data and do something. Because I'm not really concerned whether something is working or no. I'm concerned that when something is not working, that I will have sufficient information on many different levels to be able to dig down until I find the real cause of the problem. And that's actually the really complicated part. And that lack of sufficient dimensions in Sensu is I think the second of its problems. How to scale up Jenkins masters in a cluster as it is not designed as a microservice before. So right now, the way how we approach Jenkins at scale is to give each team, let's say, a separate Jenkins master. So instead of trying to pack everything in a single master, and then worrying about why is it slow and we need to scale it up and how we're going to scale, we're actually approaching that with every team gets its own master. And the reason for that approach, among others, is that now with containers, it's relatively straightforward and easy to create as many masters as you want, instead of having a single one or maybe 2 or 3 instances that that are very limiting in terms of performance. And usually we choose to have a smaller number because of all the issues we have with deploying things and then configuring things and so on and so forth. But now with Docker, simply creating 100 masters, it's pretty straightforward and relatively easy. I mean, some ways are easier than others, but it should be. I mean, it's solved more or less. Okay, so next one. Could you clarify the comment of load balancer not being relevant? So it's not that, maybe I express myself badly. It's not that they're not relevant. They're very relevant, but traditional load balancers can get as far as sending requests to one of the servers, not really to applications, because almost none of the load balancers are designed to be dynamic. They're all designed, most of them, not all, I cannot say all, most of them are designed with, okay, this is a configuration file, it's static, this is where you configure where your applications are and do load balancing. Now we cannot have that approach anymore. We cannot have approach of having configuration files anymore, simply because things change all the time. And I think that most proxy load balancers are having trouble to keep up with those ideas, and they're having trouble to adopting service discovery as a standard way of finding out where services are and so on and so forth. And specifically, I was specifically thinking mostly about load balancers like those with hosting vendors like Elastic Load Balancer. Now, the good example of something that is really going in that direction is, for example, Traffic. Traffic is a good example of something that is built from ground up with that elasticity in mind. So we always end up having 2 load balancers, one outside of the cluster that has a single purpose of forwarding requests to one of the servers, and then another one inside the cluster, like Ingress, for example, that is forwarding requests from any of the servers to wherever one of the replicas of the application are. And they need to be much more dynamic than those on both. So next one from Andrew. What are typical SDNs used in this setup? So SDNs are used basically for service discovery combined with networking. So a service A only knows that there is a service called B, and will send a request to service to a dynamically created DNS called B, and it's up to software-defined network to find out where that service is just by knowing its name, and that location of that service is changing all the time. So it's basically it's if you want, like combining IP tables with networking and a proxy into a single thing, and you get some kind of software-defined network. That, don't quote that as a definition. That's just the first thing that came to my mind. So from Stefan, do there already exist some implementations of this event listener? They do. So for example, in case of Kubernetes, for example, if you check the code of ingress controllers, they're all adopting that. Actually, all Kubernetes controllers are adopting this approach, that events are published to Kubernetes API, and different controllers are listening to the API, waiting for the event they're interested in to come in and do something. There is, in case of Docker Swarm, there is my own Docker Swarm listener that does something similar, and there are many others. But it's enough if you look at Kubernetes architecture and specifically look at what controllers do with its API, and that's basically that concept. An event is published, something is listening for events, and when the right event comes, does something. Rajiv, the Viktor book on DevOps Toolkit only gives steps for swarm-based pipeline. Is there some code base where I can get the Kubernetes counterpart of this? Yes, Rajiv, I'm 80% finished with the Kubernetes book. You can get it today on LeanPub, or you can wait until it's 100% done and search for it on Amazon. LeanPub is better because it gives you updates all the time instead of having one version of the copy forever from Amazon. Then Steve, I'm not familiar with Prometheus. Can you talk more about how it is used and what metrics it tracks? So the way how Prometheus is a pull system, which if you asked me a couple of years ago, I would say that pull systems were horrible, because figuring out where everything is extremely complicated. So I prefer push system. But now, since software-defined networking came in and many other goodies that we have today in a cluster, pull is actually becoming more prominent solution, I think. So Prometheus is a pull system, and it pulls metrics from whichever sources you tell it to pull. So let's say that it can pull metrics from Kubernetes API. And Kubernetes API has all the information about all the containers that form your that are deployed to your cluster. And those metrics are in a time series format, meaning that there is a name of a metric, whatever that name is. It's completely free form. There is a value, and there is a certain set of labels that you can use to fine-tune your searches later on. So it's just key value with a label type of format. And so periodically Prometheus would query some endpoints. Let's say every 15 seconds it would ask some endpoint, give me metrics. Let's say metrics about a server, and it would return CPU, memory, and so on and so forth. And Prometheus would store it in its database. It's a very efficient database, especially since not too long ago Prometheus released version 2.0 that made it even more efficient, probably most efficient database right now. I'm never sure whether I answer enough or not, so just ask follow-up questions if that's not enough. From Prasant, in a cluster, does ELB needs to configure to point to only one node? No. So ELB should point to all the nodes, or at least more than one node, and combine it with health checks so that it ensures that request goes to a healthy node. Now, from perspective of container schedulers and software-defined networking, it does not matter which node receives request, because software-defined networking will pick up that request and forward it further. So the only prerequisite of those clusters is that something needs to guarantee that one of the servers, whichever it is, receives a request. And that's the goal of external load balancers. Just make sure that that request gets somewhere, does not end up in a node that is actually dead. And pointing it to one node would be very bad, because if that node goes down, by the time ELB discovers that the node is down and reconfigures itself, you would have some downtime that can be a millisecond or seconds or minutes, whatever it is. So we always speak in numbers of 3 for everything. So at least 3 nodes for something, and then at least 3 for that and 3 for that. From Nick, also, what SDN layer are you proposing on AWS, or is just Kubernetes? Oh, that's a question I cannot. I mean, it is always Kubernetes today, assuming that you're having a Kubernetes cluster. Now, I cannot propose. I don't want to propose a specific one because there are like probably like 50 among very popular ones, and God knows how many less popular solutions you need to pick from. But in doubt, if you're in doubt, start with KubeNet, which comes out of the box with Kubernetes, and then with enough time afterwards to explore different solutions like Flannel, for example, or Flannel. Yeah, Flannel would be one good solution. I don't want to mention much more because there's really a lot of them. But KubeNet is great, and it works pretty well as long as you don't have more than 50 nodes inside of your cluster. If you have more than 50 nodes, at least on AWS, then KubeNet will reach its limit, and you will need to go for something like Flannel, for example. So, Paul, what do you mean when you say that the infrastructure is ahead of services? I think that self-healing, like what we have in AWS, for example, with auto-scaling groups, let's say, exists longer than software equivalents or equivalents on application level. Kubernetes, Docker Swarm, and similar tools are still fairly new. When I say new, I don't mean it's new, don't use it. No, please do use it. But I think that on those topics, simply infrastructure like AWS especially started earlier than software. And I'm not saying that software did not have those things before containers, but I think that containers are the first case where that actually truly has a chance of working well. What is the Prometheus? Paul, I think I already answered that. If I didn't, ask me again, and I'll try to answer it better. Paul, what is your opinion on Swarm versus Kubernetes when you use one over the other? Okay, so this can be a very long discussion. So I'm going to try to be very brief. So I think that Swarm is more user-friendly, and I think it provides a much better user experience. It's much simpler, and it simply works out of the box. Now, Kubernetes is much more feature-rich, and it has much bigger community support. And when I say community, I mean not only open source community, but also third-party vendors. So if you're interested in who has more features, that's Kubernetes. If you're interested who's growing faster, that's Kubernetes. If you're interested in what you can set up and learn very, very fast, and it will simply work without much hassle, then that's Swarm. That's my very, very brief comparison. It's much more than that, though. Greg, thanks for providing meta view of this, very useful. Based upon this ecosystem, what areas, capabilities do you feel need to be involved, improved? Do you have a view of what this ecosystem is evolving into? So in a very, very short future, I think that where it's evolving is towards self-adaptation. Now, quite a few things that I showed, I think will stay true for years to come on principle level, but we still need to do quite a few of those things ourselves. I think that, for example, Kubernetes will at some moment in time do that, and it is already doing with horizontal auto-scaling. But it's in very early stage, and it really provides very limited use cases. So I think that more or less what I explained today, especially on application level, is where platforms will be moving towards, instead of us setting them up through many different tools and processes. And further than that, I think that resource isolation is still a very problematic topic with containers. We're probably going to see unique kernels taking over, and especially, at least for some use cases, if not for all, and so on and so forth. To me, it's very hard to predict anything more than half a year from now, because things change so fast that I cannot see more than a couple of months ahead, I think. From Kyung, following the scaling up master question, do you keep the persistent data Jenkins home in a cluster such as Kubernetes? Any best practice? So everything you need to keep, if you go back to infrastructure level, all stateful services that rely on file system need to keep things on an external drive. That can be EBS. In case of AWS, it can be EBS or EFS, and other providers have other solutions, or if everything else fails, NFS. Now there are interesting new solutions, I think, coming up. Like, for example, GlusterFS allows you to store locally instead of on a network drive, but whatever is stored locally is replicated across servers, so that even storage is local, that is replicated, so a failure of a server or a group of the servers does not mean lots of data. I'm not 100% sure whether those drivers like GlusterFS are a replacement for all use cases yet, but definitely something interesting to look at as an alternative to external drive. So, but in a very general terms, I would say you need always to store it on a network drive, NFS, EBS, EFS, whichever the technology is available to you. And depending also further on, you need to think about things like, do you need speed or do you need availability across multiple zones and things like that. So, but it's always a network drive. How to do from Kumaresan, how to do queries, how to do database queries Jenkins pipeline. I'm sorry, but I don't think I understand the question. So if you can write it again, I'll do my best to answer it. From Dan Trunter, sorry if I missed this, but where does encryption across the wire terminate in this architecture? At the ELB, or is there a worker within Kubernetes to handle encryption, decryption? So it can be both. It can be SSL can be offloaded on ELB, or it can be offloaded inside of a cluster. Personally, I prefer offloading it inside of. I prefer offloading certificates on ELB, and then the communication within SDN network can be encrypted on its own if needed. Now, there is encrypting communication within SDN has obvious performance penalties, so it's not something that we should always do, but only if you really have to. Steve, follow-up. Prometheus follow-up. Can you export data to do other processing on it with Python or R, or does it have a scripting language included? Yes. So Prometheus, if you focus on it, so Prometheus has libraries for some maybe 20 languages that you can use to export metrics specific to your application. And even if your language, so Python is most likely supported. I would guess that R is not. I haven't checked. But if it's not supported through official library, it's fairly easy to write it yourself, because all you have to do is to have an endpoint, let's say /metrics, and you respond with metrics to that request. And metrics are key value labels. That's it. It's always the same format. As long as you can output something in that format, you're good to go. Now, of course, with libraries, you have additional kind of simplification of things, but ultimately it would be easy to do it without any library. So Amado, what are your thoughts on Kubernetes versus ECS and Fargate? So ECS, I think that's a failed experiment that hardly anybody would deny. So the real question is, I think, thoughts on Kubernetes versus Fargate. And so one of the things I love about Kubernetes, it doesn't have to be Kubernetes, any scheduler, Kubernetes Form or Mesos, is that they're a layer of abstraction between my hosting vendor and my applications. So I can deploy my applications to any Kubernetes cluster running anywhere, on-prem, on AWS, Azure, GC. I can decide that I don't want this vendor and move to another vendor. As long as there is Kubernetes cluster, I can run my applications. And I think that's a great advantage. Now, Fargate is designed to lock you into AWS. And I personally think that kind of diminishes one of the big values behind Kubernetes. Now, if you're married to AWS and you're sure that you will be always there, and you're sure that they will always be able to follow the industry and all those things, then probably it's a great solution. I did not put much. I did not dedicate much time exploring it because I think that's simply it's too much of a vendor locking for my personal taste. Joshua, I would like to map out our workflow to fit your diagram. What are your suggestions for resources to help me out, our processes, evaluate our current tools, and identify what we need and how to apply to the model you presented? Ooh, I cannot really answer that. It's kind of I would need to the answer would need to last for an hour. Check my books, that might help, or my blog post. Learn Kubernetes and learn the tools in CNCF, Cloud Native something. And that's a good start, I think. I mean, sorry, if you first learn Docker, you cannot go to basics first. But I really don't know. I would need to know where you are right now, what you have. I would need to know what your current knowledge is, and then I could be able to answer the question. And I would need more time. Sorry for that, Joshua. So from Slavomir, could we find how to configure all tools, Kubernetes, Ingress, DNS in your DevOps 2.3 Toolkit book? I'm looking for one working example of system which proves self-healing system is possible. No, you will not find all those answers in DevOps 2.3, and the reason is very simple, is that the book is almost finished, but the subject is so vast that I could not fit everything in 400 pages. So you can think of this book as everything you should know about Kubernetes that is not everything non-advanced for Kubernetes. Kubernetes Kickstarter or something like that. It goes deep. It's very hands-on, but it doesn't go that far. Actually, sorry, I misread. I thought you were talking about self-adaptation. Self-healing, yes, you will learn about that in the book. Self-healing is relatively easy. So yes, all those things you will see from 2.3. The part about self-adaptation and part about monitoring, that is coming in 2.4, which will start. First chapters will be available in 2 months from now, something like that. Will the presentation be made available? Yes, I will send the link after this to Max, and Max will send it to you all. And Max, you tell me if I'm saying something that is not correct.
That is correct. Just real quick to let you know, Victor, we're just beyond the hour, so to be wary of everyone's time, why don't we do one more?
Okay. So, Prasant, do you recommend running Jenkins in master slave, or master is enough, especially considering Docker makes it easy? So I would recommend that you run only master as a long-running application. never run your jobs inside of your master, but use containers. Create containers when you need to run a job, build, and destroy them afterwards. Depending on technology platform you use, for example, for Kubernetes, you will use pod template, which would create pods which contain containers, run something inside them, and then it will destroy them. If you're running Docker Swarm, use my own container. I have a Docker image for doing something similar, and so on and so forth. That was the last question. Sorry, guys. I really a lot of questions. We cannot answer them all, but you can find me.
Yes, if we weren't able to get to your question, Viktor did put his Twitter handle on screen earlier at Farcic, and then I put my email in the chat. So by all means, send it to me, and I'll help put you in touch.
Yes,
otherwise,
that's me.
Yes, perfect.
Sorry.
That's all right. Otherwise, we are a little over the hour, so I just want to be respectful of everyone's time. So I want to say thank you to Viktor for this presentation. Thank you to all of you for your great questions. So we filled up quite a lot of time with questions and still have plenty more that we weren't able to get to. So yeah, let me know if you would like to have something answered we weren't able to get to, and I look forward to hearing from you all again soon. Thanks, Viktor.
Thanks, Max. Thanks, everybody.